Hi, welcome to this course on perceptual optics. In this class, we are going to look first at physical and geometrical optics. There will be a separate video to look at Voxel Theater, in other words, how is a 2D retinal image converted back to 3D. We will consider bank necessities, in other words, the fact that we understand shapes in a invariant sort of matter regardless of their orientation, their scale, their location. No matter what region of retina or visual cortex it's hitting, we still understand it. We'll talk about frames of consciousness, which is basically talking about that at some level of temporal zoom, there's going to be discontinuities because it would be impossible to have a consciousness that is completely continuous because like every millisecond or every nanosecond you would have to have information on the full 3D scene, which we don't have. I mean, the retina has a shutter speed of about 50 milliseconds, I think it is, or maybe 1/50th of a second. But it's whatever it is, we'll get to that. And so there's certain minimums, and so in the end, consciousness has to have a somewhat discontinuous nature or frame rate, so to speak. We'll talk also about schemas, which is like you've got the real world schema, which is your body, the stuff around you, this mental representation that we have of the things around us. You have the imagination schema, which is where, if you're listening to language, you have mental imagery of the concepts or of the person speaking. And then we'll also examine static and sequential memory. Light is emitted when an electron wiggles or experiences acceleration. Cyclic vibration in the range of 4 to 7 terahertz. That's trillion vibrations per second underlie colored light. And light propagates outward spherically at 300 million meters per second. And here at the top, you can see an electron, and it's moving this way, causing a compression in the electric field and a rarefaction on this side, and then it will vibrate back the other direction, cause compression there, refraction here, rarefaction, and then the disturbance gets propagated outwards at the speed of light. This is your visual path, so the image comes in through the cornea, pupil, lens, inverts, and comes to the back of the eye. It goes through the optic nerve to the lateral geniculate nucleus of the thalamus. It then follows the optic radiations to the visual cortex in the back. Light is traditionally understood as a transverse wave as opposed to a longitudinal, like sound. Here you can see sound radiating outward in these circles, and it radiates out in spheres. So, in a sense, light is a longitudinal wave, if you want to think about it like that, because it does propagate out like this, but it also has this component where it's a straight line. So it's like straight lines coming out in every direction. And so it's kind of a complex thing, but you can kind of think of it as having a little bit of each component. These are the Linear-Vickert equations. I think I'm pronouncing that correctly. And these just show you that both electric fields and magnetic fields arise from the same phenomenon, namely an electron oscillating or accelerating. And so just based off of the position, velocity, and acceleration of one electron, you can calculate with these equations what the electric and magnetic field that some other charge at some other location is going to fill based off of the first charge. Let's see here. So basically a stationary or moving charge has a dressing field that just kind of hangs around it, and an accelerating charge emits a radiation field at the speed of light. So when the charge is stationary or moving at constant velocity, Linear-Vickert potentials describe the electric and magnetic dressing field. And when the charge is accelerating, these same equations account for the electric and magnetic radiating field, which propagates as an electromagnetic wave, and at certain frequencies it is visible light. So the charge's addressing field that hangs around it, if the charge is right here and you're going away from the charge a small amount, most of the field is very close to the charge and it drops off. If you put it on a log scale, you get a straight line. This is an equation that you can use to describe the addressing field. Einstein's special relativity also considers electric and magnetic fields to be coming from a single origin. If we have a stationary charge here, a stationary observer will only see an electric field, whereas a moving observer will see both electric and magnetic field. If we had a third accelerating observer, then they would experience the Unruh effect of particles. So one of the key results of Einstein's special relativity is the Lorentz transformation, which describes how the electric and magnetic fields transform between different inertial frames. That would be like the stationary guy and the moving guy over here. And it further highlights the interdependence of electric and magnetic fields in their common origin. Quantum also sees electric and magnetic fields as arising from the same thing. It's the interplay, or it's the common origin in charged particles. Quantum is going to consider the addressing field to be virtual photons, and it's going to consider the radiating field to be real photons. And it's just quantizing the electromagnetic radiation, at least for the real photons. It's quantizing, at least to this concept of individual photons, as elementary particles that represent quanta of the electromagnetic field. So all of these different ways that you look at it, the electric field and magnetic field appear to be arising from one effect of a charge accelerating. Also, when light is emitted, it's emitted in expanding spheres, and when it's captured in decreasing spheres. So if we sum up all the points along this radius, and then we move inwards towards the camera, let's call this camera over here, we move inwards towards the camera, we have another sphere that's smaller here, we have another sphere here that's smaller. We're just gathering whatever voxels are emitting light, and it all comes into a point. So these, if you wanted to be really technical, it's kind of like a summation of different times, because since light takes a little bit of time to travel, these are happening like, a nanosecond or whatever it is apart. So this 2D image is kind of a summation of different times, but they're so nearly simultaneous that we're usually going to just consider them as simultaneous. But when they come down to this point, you still have all the 2D information of the world that you are sampling, but you lose the depth. Now, with perspective images like what this creates, you still have a clue to depth, because farther objects, like when this candle is farther away, it's going to take up less angle, versus if it's close, it's going to take up a larger angle. So based on the relative size of things, farther things are going to be compressed, and so you can have a clue in a perspective image as to depth, but the actual specific depth information would have to be recalculated. And this is just representing a pinhole camera where we have a hemisphere that's a black container. It's closed off to the environment except for this one little pinhole here. It's letting all these different orientations of light rays come in. They're coming from all these different voxel points out in space, and they're all going to come to a point. So the 2D image information is contained in this zero-dimensional point because of the 3D vector orientation of each light ray. And each light ray is also carrying intensity information, color information, like the frequency in other words, even polarization information. So you have all this information contained in this zero-dimensional point, and then it gets spread out, and each vector orientation lands on its own specific rod or cone in the retina. So pinhole cameras are actually pretty useful for understanding vision. If we have this candle and we have certain points on the candle, then each point is emitting a whole sphere outwards, but it's only emitting a certain direction as it goes through this pinhole, and then we can keep the rest of the camera inside is closed off except for this. It's black except for this hole. So these rays of light then make this image flip and appear on the back side of the camera. So you actually don't have to have a lens to produce an image. Just every single point in 3D space already contains an image, which is pretty startling to think about. But it already contains the image, and you just have to give it the tools to spread out, where we can have these rays be converted to pixels on an image that makes sense to us. So it just says, when examining the physics of photography, one must first conceptualize the existence of spatial points within the environment and a pinhole aperture, establish a connection between each point in space and the pinhole, and subsequently extend those lines to reach the camera sensor located at the back of the device. That's exactly how the eye works also. Of course, it does have a lens, but we'll get to that in a second. The benefit of pinhole lenses or openings, they're not really lenses, is that there's no need to focus. However, a little blurriness is inevitable because the aperture is always going to be a little bit too large, or if you got it down where it would be small enough, you'd have a diffraction effect start to take over, and the diffraction would cause muddiness in the image pixels. And also a lot of light is required to get a photograph with a pinhole camera. But these three are taken with a pinhole camera, and you can see it's decent. You know, it's not as clear as you're used to, but it's kind of a nice, kind of soft, result. So in summary, one pro of pinhole cameras is you don't have to focus anywhere. Everything's going to be equally in focus or equally a little bit muddy. Con number one, it requires a very substantial amount of light. And con number two, you cannot achieve perfect clarity due to diffraction effects at the very small apertures that would otherwise produce clarity, like about 0.1 millimeters. So an optimal aperture size is about 0.35 millimeters. These are just a couple examples of pinhole quote lenses. There isn't actually a lens in there, but you can adjust how far the pinhole is from the image sensor with one of them, and you can also adjust the aperture size with the other one. I forget which is which. Lenses will allow more light to get into the camera because we're taking the pinhole and increasing it to a large opening. But as we do this, we create another problem, because now, instead of having a single central ray of light from each point obediently coming to the correct spot on the back of the sensor, we now have an entire cone of light rays coming from this one point. And if we didn't use a lens, they would just spread out into complete mud on the back side of the image sensor. And this one point would now be spread over half of the camera's sensor, and so would all the rest of the points. Just be complete mud back there. So what we have to do is, this lens has a convex shape and it has a certain refractive power. And what that is going to do is, it doesn't have to do anything to this central ray, and it in fact does not do anything to it because that's already okay. But as you increasingly get to larger radii from that central pinhole, you are having to increasingly bend or refract these light rays so that they end up coming back to a point. And so lenses enable increased light intake by widening the aperture, and as they emit a conical spread of light from each point in space, they must focus or refract the light rays to converge at a single point on the sensor. So front focal distance here, we have an eyeball that's looking at an object or a point that is 5 centimeters away. So this created this sphere shell focus. If we could see in all directions, you'd have a sphere shell. Obviously, we can only see the front part. So we've got a couple of points here that by the time the light rays from that point reach the pupil, they have formed a cone that needs to be refracted, inverted back to the other direction so that it can become a point at the back on the retina. So from this blue central ray to the edge of the cone is alpha, times 2 is the two-dimensional complete angle of the cone, and then omega is the three-dimensional solid angle subtended by the cone. And focal power is expressed as 1 over this back, 1 over the front distance and 1 over the back distance. So here, 5 centimeters, we need to express it in meters, so 1 over 0.05 plus the back distance. Let's assume this is 2 centimeters, so 1 over 0.02 meters would give us 70 diopters of focal power needed. And this is a little bit higher than what humans have. I may be a little bit inaccurate on the 2 centimeter assumption here, so we may actually be able to focus 5 centimeters, 2.5 inches. But the point is that roughly 70 diopters, we have 50 to 55 or 50 to 60 diopters total. So the cornea provides most of your focal power, actually, 40 diopters worth. The lens, when it is fully stretched, has 10 diopters. So 50 plus 10, or 40 plus 10 gives you 50 diopters, which is sufficient to focus at things at infinity. That's the easiest thing to focus on. Then as you relax your lens from being stretched out, it becomes more spherical and it has more focal power. And so it bumps up to 15 to 20 diopters of focal power now so that you can focus on things closer up. So we will go on to the next slide and consider some other angles. Here's some other focal lengths. Obviously 1 centimeter or 3 centimeter is really closer than you're able to focus. It requires 83 diopters, 153 diopters. 1 meter away would require about 51, so just a little bit more than infinity to focus that. It would not be very hard to focus. These closer distances are becoming increasingly difficult to focus. So nearsightedness, which is myopia, is the eye has too much focusing power. So that's like my case. I have to wear contacts or glasses to reduce my eye's power because it's too powerful. And so it's I can't see things far away because it's working too hard. So you basically have to like take away some of its power, and then you're able to see clearly again. Farsightedness would be the opposite. This little drawing showing you light coming into the pupil, going through the lens. It's going to land on the retina. Rod, see at night. Down below it said cone, see color. And my video is blocking that. Sorry about that. So focus, there's 2 different concepts. So there's the distance from the lens to the object. That's your focal distance, or your front focal length. Well, let's just call it focal distance. Okay. And then from the lens to the back of the camera to the sensor is your focal length, back focal length, in other words. So you got focal length, and a lot of times if you hear about camera lenses, they talk about, oh, this one has such and such focal length. Okay, well that's what they're talking about, and it's just a useful way of talking about how much focal power. Well, we'll get to that later. I may be misstating that, but we'll get to that in a second. And focal distance again is just distance from the lens to the object. So focused breathing is a situation where if you have a 100 millimeter telephoto lens, then it's designed to focus starting off at infinity, and as you push that lens farther away from the sensor, all the way up to 110 millimeters or 11 centimeters, so you've increased its distance from the sensor by 1 centimeter. You've now gone from focusing on infinity to now focusing on some subject that's 1 meter away. And you can see the whole scale, whole gamut of values there. But as you did so, you also shrunk the field of view from a diagonal angle on a full frame camera from being 23 degrees to being 20 degrees. So this graph illustrates the same concept, that when the lens is 100 millimeters away from the sensor, it's focusing on infinity. The blue line shoots up to infinity. And then as you push that lens away from the sensor, what you're focusing on, your focal distance, is decreasing till you get all the way down to like 1 or 2 meters down here. And at the same time, your field of view, the red line, is shrinking from 23 degrees all the way down to about 20 degrees. And the only way really around that is to buy a super pricey Cine lens that has a way to essentially eliminate that focus breathing, so that if you're shooting a video shot and you want to change the focus from something in the background to something close up, the field of view of the scene doesn't, change at all. It just stays steady, which is kind of nicer on video to have that steadiness. So talking about photography variables, we have shutter speed. How long do you leave the sensor exposed to light for one picture? You can vary that from like 1/8,000th of a second on a Canon 5D to like 30 seconds, but here it's just showing like 1/15th of a second to 1/1000th of a second. When you have a very fast shutter speed, you can freeze motion. So like if you're shooting a picture of a helicopter, you can freeze the motion of the blades so that it looks like it's not, the blades are not turning. And then if you take a longer exposure, you can blur things, or if you're shooting the stars at night, you can get star trails with like a 30-second exposure, or do several of those and then combine them. You can get a nice long star trail. Aperture is just how big is the opening in the camera. You can go from f1 to f32, f64. This is going to be a very small opening. This is going to be a very big opening. When you have a big opening, you're going to have a very shallow depth of field, which means that only a certain range is in focus and the rest is extremely blurred, which can be advantageous for bringing focus to a particular subject's face, something like that. But it can also be annoying in some cases, so sometimes you want the smaller opening size. ISO is just artificial gain sensitivity of how sensitive do you want each sensor on your camera to be to light. If you want it extremely sensitive, make it a little bit of noise, but you're also able to shoot pictures at nighttime. And you crank it up high enough and use like a somewhat long exposure, you can make it look like daytime in the middle of the night. Stuff like that. Metering modes is just determines how the camera is going to measure light to calculate the correct exposure settings. Depth of field, we talked about that. So focus distance we already talked about, and you vary the distance from the lens to the sensor, increase that distance to decrease the focus distance if you want to focus on something closer up, in other words. Field of view is a good chart showing you different fields of view. You've got a 12 millimeter lens, you're going to have a wide field of view. They say human vision is about 50. I kind of disagree. I think it's more like 24 or 12, but that's often a common lens length to shoot at. Once you get to 100 millimeter, 400 millimeter, your telephoto, you're really zoomed in. You also notice that as you get larger, you're getting to more of a flat focus plane. And when you have a smaller number, larger field of view, it's almost like a sphere. And in fact, all of these are sphere shells, but it's just as you take a little tiny chunk out of that shell, it's essentially a plane. It gets down to being very close to a flat plane. So telephoto is zoomed in, wide angle is zoomed out. And there's also white balance, so you can set the color temperature in an image to produce accurate colors. Different light sources have different color temperatures, which can affect the appearance of white objects in the photograph. So if you set the correct white balance, like if you're shooting outside and you set your camera to sun light, then it's going to accurately record the whites, or more accurately. And so you can adjust that setting. You can even just set it, like if you know what degree Kelvin it needs to be to match a particular lighting environment, then you can do so. Cameras also offer different image modes like JPEG and RAW. So a JPEG for Canon 5D Mark IV is, I think, an 8-bit for each sensor pixel. It's going to have 8 bits of information for each color channel, so red, green, blue, and I think also intensity like black and white. But for each of those channels you get 256 increments, because 8 bits in binary is just like 8 zeros or 8 ones or some combination of that. So there's 256 combinations that you can make out of 8 zeros and ones. If you add just a few more 8 zeros and ones and do a 14-bit for each channel, you get like 16,000 increments or bits of information or unique patterns that you can represent with zeros and ones. So it's kind of this, I don't know if it's exponential, but it's this, like, as you add a few more bits to the channel, you can tremendously impact how many levels of resolution of color or intensity that you can have. Of course, it's going to take more image size to store a raw file. So there's trade-offs. So in this example here, they did not change the lighting. So they used the same lighting source, but they changed their camera setting from warm to neutral to tungsten. And of course, it produces a different image each time because it's trying to adjust to a scenario that doesn't exist, so you end up with these different colored images. Videography adds mostly just the frame rate, but also you want to have a little bit of motion blur. So if you're shooting at 24 frames per second, you probably want to have 1/50th of a second exposure so that you get a little bit of blur. It makes the video a little bit softer to watch as you're going from frame to frame. If you're shooting still photography, a lot of times you want to bring that number way down to like 1/200 or 1/400 or something like that. But videography, you want to keep it a little bit blurry because the dynamic or changing frames, somehow your mind is able to not notice the blurriness, and it actually kind of adds to it. Video is also going to require synchronized audio. It's going to require attention to continuity between shots. It's going to have video codecs, compression, and it's also going to have things like color grading, sound design, video editing to make the video look nice. So perspective versus orthographic. Anytime you're shooting with a camera or anytime images are coming into your eye, that's perspective images. And an example of orthographic would be like if you had a set of blueprints and it's a bird's eye view of the layout and all the lines are exactly accurate. So perspective and orthographic. This is showing you that when you have a perspective image, if you're right here at the origin, you're looking outwards this way, the further things get, the more they get compressed. But it's getting compressed at a decreasing rate. So it's kind of like diminishing returns. Like when things start getting really far away, the further they get, you're not going to see a whole lot of change, and then you can't really extract as accurate of depth information from it. So if we consider the visual field in terms of this theta phi gamma, it can actually be pretty useful. So although it's tempting to envision your visual field as a flat image with horizontal and vertical pixels, it's more helpful to think of it as comprising vector directions. The pupil serves as the convergence point, with the central foveal region being a vector aimed at your focus. Other pixels are accessed by accessed by deviating a specific number of theta or phi and gamma degrees from this central vector. So basically, I'm looking straight through this point in the middle, and things that are further this way are degrees of theta, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 20, 30, 40 degrees theta, all the way over to 90 at my ear, which I can't, or I can just barely see that region. And then going vertically up, you have degrees of phi. And then if you were to start here at the ear and go up towards the top of the head, that would be gamma. So this is just one way to measure things, but it's actually pretty useful because let's say you're driving down the road and you see a sign, speed limit sign. The sign is always 8 feet tall, but it grows in the height of theta, so it starts out at maybe 1 degree when it's far away, and it's growing until it's like 5 degrees or 10 degrees, and as you pass it, then it starts decreasing back down. And so this is kind of an objective way to talk about our experience, which is dynamic and which changes based on our location in the environment. So it's still a pretty useful thing, and the thing is too that humans can differentiate 1/60th of a degree. So if you hold your pinky at arm's length, then the fingernail will be about 2 degrees theta, or if you turn your hand this way, it'll be about 2 degrees of phi. And then the sun or moon will take up about half of that distance, and we'll see that in the next slide. But if we think about like theta as being 360 degrees from here all the way around the back side of my head and then coming back around here, and phi is 360 degrees and gamma is 360 degrees, that's interesting. But another thing that's interesting is the solid angle subtended by the entire sphere, which is 41,253 square degrees. And so that's just like a single degree of theta, a single degree of phi. Okay, it makes that little pixel. And how many of those little pixels are there around us if we were able to see in all directions? Well, it'd be 41,253. Of course, you could divvy it up into smaller increments or greater increments. But this is just a useful thing to consider. It's a useful number to hang on to. And we will show that, using some of these assumptions, we'll find that humans can probably discriminate about 5 to 7 trillion voxels, and maybe quite a lot more, depending on what assumptions of what our finest granular discrimination is. So if you hold your pinky out at arm's length, then it's about 2 degrees of theta in width, and you'll notice that the sun and the moon are about the same size in terms of theta and phi, how much they take up on your retina. And so people often say, well, just hold your pinky out and you'll see that the sun is half of your pinky, or the moon is half of your pinky. And so the sun and moon are about 1 degree wide. I think the actual number is 0.6 degrees, which can change a little bit as the sun gets closer or farther away from the Earth or the moon. But basically about that. There's going to be another eclipse. This one's from 2017. There's going to be another one in 2024 that goes from Texas all the way to Maine. About 4 minutes of totality, as opposed to, I think it was about 2 minutes of totality in 2017 eclipse. So definitely recommend that. It was a really powerful experience. So if we consider perspective and orthographic, this top view is kind of confusing because it's a top-down orthographic representation of a girl's perspective view of a hallway. So kind of complex there. But to this girl, the front of the hallway, which is 8 feet wide, takes up 20 degrees on her retina horizontally, and the back of the hallway, which is also 8 feet wide, takes up only 5 degrees of horizontal theta on her retina. So you can see that just by varying this radial distance, the same size can occupy a changing amount of distance on the retina. and also within perception, the back side of the hallway is going to look smaller than the front side, even though we know that both front and back are 8 feet wide. Same thing with the height of the hallway. It's going to appear taller on the front end and shorter on the back end, even though, again, both are 8 feet tall. So to the girl, she sees this on the left. She sees the back end of the hall compressed. The front end is larger. But if we placed a orthographic camera, if someone were to actually make that, which would be, in this case, an 8 foot by 8 foot camera sensor and a bunch of straws, like drinking straws, tiny drinking straws pointing straight. So basically forcing that only straight light rays can come and hit the sensor, then you would get an orthographic image that looked like this, and this is both the front and the back of the hall. And so you can't distinguish anymore between front and back because they're occupying exactly the same space on the orthographic image. As far as I know, nobody has tried to make an orthographic camera, but I think they definitely should because it'd be pretty cool. So the whole thing of this is that consciousness, we understand 3D depth. We don't get confused. Like if we see these lines going down the hallway, we know that's it's going in the depth of the hallway. It's the intersection of the wall with the ceiling right here. But to a computer, oh, you're just drawing on this fronto-parallel plane. And I think my camera's blocking part of it. Sorry about that. But anyways, the computer doesn't understand, whereas we do. So we're going to have to consider how the brain does that. And we should define allocentric as the consistent 3D isometric representation of the environment, such as a hallway, with accurate dimensions. Egocentric, on the other hand, refers to the 2D perspective image derived from the 3D model, which inherently depends on a specific viewpoint in the 3D perceptual space, indicates the observer's location. This distinction holds true for mental imagery, where a 3D mental space, allocentric, and a 2D perspective image, egocentric, serve to position the mind's eye within that space. The uniform 3D isometric depiction of reality or imagination forms a skin or schema. So again, allocentric is similar to isometric, is similar to orthographic, 3D boundaries or skins, 2D edges or perimeters. Egocentric is similar to perspective, and it's usually 2D.